Okay, so there's lots in there. Now what we're going to do with this section here is I'm going to give you some example, which, have you guys actually, I believe Anne was doing like some talking thingy on the native fish. Have they been introduced to native fish already, Eric? Do you know? I know that Eric, Anne did a recording on the native fish, did you?
Yes.
Have they seen it, or?
I'm not sure if it's available on the web. Anne did a recording, but there's some editing to be done, and I'm not sure if it's on the Google Drive.
Yeah. Well, there might be a lot of repetition with this one here. So we use our example here of a native fish population here. So take some time to sort of read up about this problem statement. And the idea is we're going to build a Bayesian network of this system and start doing cool things with it. Everybody good? Okay. Basically, we've got our croplands and we've got a river going through there, and we're worried about what actions we're going to be taking on the croplands and how that's going to impact the native fish population there. And there's a whole lot of other details in here that are interesting to the model as well. So we go back to our definition here, and we're going to go for each of these different points here, and we're going to start building our Bayesian network. So this is my process for building Bayesian network. So our first bit is a set of random variables. So we want to go back to, we're going to go back to our problem, actually identify what are the random variables that we want in this problem here. First of all, we've got these definitions of what nodes and values are. So we have our node, which is a random variable, which can take on any number of states. It could be discrete, as in it could be true or false or high or low, or it could be a continuous distribution as well. So within Bayesian networks theory, we have all that stuff. Most of the tools support only discrete Bayesian networks. And there's a reason for that, because we can do that exact and fast, and it's a lot easy. Generisk is one of the ones that actually can handle continuous variables, and it does that by doing some smart, fancy thing to discretize the continuous variable. In Netica, and for the exercises for this session here, we're just going to look at discrete variables, and I think for your BARD project you're going to be mostly involved with just discrete variables there as well. So what do we got? We've got different types of discrete. So we've got Boolean, which is generally our easiest one. So this variable is either going to be true or false. The light is on is true or false, or the crop yield is high is true or false. We can have categorical ones. So what's this color of my shirt? Is it orange, red, or blue? We can have different ordered ones. So for example, here with this native fish abundance could be a high population, a medium population, or a low population. We could have integral ones, which we don't really use very often. I very occasionally use them, which each of the, we might have a number of values for each of the states. So rainfall could have something from 1 to 2,000 states values. Or what we often do is we use a discretized range. So we'll break up rainfall into some range of possible values, so from 0 to 50 millilitres a year, from 50 to 200, 200 or greater. Now, when we go to native fish, there's different sort of ways that we might do this, but generally what we're doing is we're going through and identifying all the nouns in here. Now, I imagine that this is stuff that you guys are going to be talking a lot about in your projects, so you're probably going to find other hopefully better ways to do this. But so what I might do here is I might go through and actually underline or bold, in this case, all the different nouns within there. So we've got a river system, we've got tree line, banks, native fish population, cropland, drought conditions, pesticide, rainfall, water flow and connectivity, and a whole lot of other ones in there that we just didn't bother highlighting. Now, the reason why we do this is because these nouns are good indicators of what our random variables are going to be. We're interested in, well, particular about what our native fish population state's going to be, what our cropland is going to be as well. There's these different things that might be, well, you know, what we're looking to sort of measure and affect, which is a pesticide use there, and other things like rainfall and drought conditions. I might go through there. So we identify a few of the endpoints. So we want to know how the system, the ecological system is going there, which is measured by the native fish population and the tree conditions around it. We've got a whole lot of water-related stresses, so how's the flow going through the river, how much rainfall there is, and whether we're in a drought condition. These are all different things in there. There's some pesticide-related stresses there, so whether we're actually using and how much pesticide we're using on the crops, how much that pesticide is actually ending up in the river, so what's the concentration in the river. And there's other stuff there about crop stuff. Now, often what we do with Bayesian networks, the temptation is to get all our variables and chuck it all into one big Bayesian network, but one of the things that we advocate is actually some iterative development. So start off small, especially when you're doing your first Bayesian network, and there's certain things like crop stuff that we can actually build into the Bayesian network later on. This keeps the things manageable. So for now, we're just going to deal with this ecological side of things, like the impact of pesticides and environmental factors on the native fish population and tree condition here. At this point, while we're picking these variables, it's usually a good idea to think about what the states of those variables are. Now, this is a good sort of check as well. Like if you can't come up with a sensible state space, then it's usually indicative that you've got the wrong variable there as well. You might change this in the future, but generally I find mostly it's pretty good. So we have some suggested ones here for tree condition. We could have a good or poor tree condition, or we could have good, damaged or dead. Native fish river flow, that's all we've ordered. So we've got a high river flow or native fish population, a medium and low. Drought, we can say is either yes or no or in a drought condition. Pesticide use ordered, rainfall has got some sort of discretized ranges attached to it. So we might be tapping into some meteorological database, which is actually just giving us out a number on millimetres. So we'll use that type of stuff with Bayesian network as well. Right, so we've got a set of different candidate random variables in here. Now, often we'll go back and change around that, drop some of them, or add some new ones as well as we go along. Generally, my first pass of that is never correct. So next thing we want to do is we want to work out the directed links between these random variables. So we have this idea that when we put a link between two random variables, what we're saying is there's a direct influence between these two different variables. There might be other pathways between variables, but when they're directly connected, it's direct. Let's... can people remember their variables that I had up beforehand? Does anybody want to hazard what the direct influences of native fish abundance are? So if I go back here, so native fish abundance. So if this is all our random variables, which variables do you think are going to be directly influencing the native fish abundance?
Rainfall and pesticides.
River flow, sorry?
Pesticides.
Pesticides, yeah.
Rainfall.
Rainfall, yep.
Drought.
Drought, yep. What about, so we've got these other ones here, pesticide in the river. So I would suggest to you that it's actually the pesticide in the river that's going to directly affect the native fish population, and the pesticide will actually affect the pesticide in the river. So we have an influence, you're correct, but we want to look at the actual direct influences there. So we can say, yes, we definitely know that pesticide use is going to affect it, but then we look at pesticide in the river and go, actually, that's in between these two different ones here. So there was a question or statement?
Why we don't have a none where we've got high and low?
A none for?
None for pesticide use or pesticide use.
Well, you could. That was just a design decision for this here. We just basically said that low is some, so none is very specific, where we might want to actually just say negligible, or as good as none might be a better way to actually do it, whereas none is kind of like, well, can we actually guarantee that there's no pesticide in the river? And do we really care if there's a really, really small amount? But yeah, those types of design, often it might be the case that we won't actually use a none, and that's is good. Fuzzy numbers? Well, you want to avoid that. Okay, so we got the so we had the native fish abundance. So we said pesticide in river. What was another one that might be a direct influence?
Like a flow?
River flow. And again, we had the rainfall was what we were saying, but the rainfall again was kind of goes through the river flow. Yeah. So then we can just go up here. So pesticide in the river, what's that going to be impacted by?
Pesticide use.
Pesticide use and rainfall, yep. And arguably we could also say drought condition because that might affect the runoff type conditions of that. Well, in this case we're saying drought is basically it's been in a drought in the past. So everything's dry, so that's going to affect how much water is going to be running off into the river.
It means that pesticide in the river is actually affected by river flow.
Sorry, yeah.
It's also affected by the river flow.
With the river flow. Well, yeah, the pesticide in the river could also be affected by the river flows because it's washing it out faster. That's another one that we could have. What about river flow?
Rainfall.
Rainfall, yep.
Tree condition will affect how much pesticide is in the river.
Yep, could do that, yep. Anybody else for another one for river flow?
Drought.
Drought, yep. Okay. What about tree conditions?
That will probably affect river flow as well.
Yep. So there's a lot of different arcs that we can put in here, but what we try to do is generally what happens when we sort of do these kind of graph type things is we end up with a really quite densely connected type of network, but then we try to be really quite discriminate and only put the ones in which are really important. So what we've said, what we decided for our one here, is that native fish abundance should be affected by pesticide in the river and the river flow. Pesticide in the river is going to be about annual rainfall and pesticide use. I did talk about drought conditions, but we didn't do that. So basically how much pesticide is on there and how much of the washing action is going through there. We've got river flow, which is affected by how much rain there is in the drought conditions. And then for tree condition here, we've got drought conditions and rainfall. Now, as we had discussed beforehand, the tree condition will often have different effects over here. So, tree conditions on the side of the river will give habitat for the fish as well. So, our fish abundance might actually be impacted by our tree conditions on the side for riparian vegetation. It could also affect the river flow, and I'm not certain how it might affect the pesticide in the river, but
Pesticides will be absorbed into the ground.
so it would absorb and extract some of the pesticide in the river. So we might have all these different possible arcs in here. But at some point we kind of just decide, is this a worthwhile arc? So generally the objective when we're creating the Bayesian network at this point is to try to keep it as simple as possible. So we don't try to put every single different influence within there, we just try to put in the most important ones here.
If you want to keep it simple, can we have a loop, let's say free condition got an influence on the river flow, and then there is a retroaction of the river flow on the tree condition?
Are you talking about putting loops within the Bayesian network? Well, we can't do, in a simple Bayesian network, we can't do feedback loops within it, even though that might actually be the case in our system, but we're going to talk tomorrow about how we might handle those types of modelling problems. But you're a good point.
I don't know if this is a bit premature, but is that related to the cost of gathering information, the value of information? Because if you've got too many, if you're too generous with your links,
Yeah.
you're going to have to gather that information
Yeah.
to feed into the tables.
Well, this is what I'm going to talk about just in about 5 minutes. But one of the things that when we're doing these design decisions, and you should see the motivation for this, is we want to be careful about how many different states we have for these nodes here. We don't want to put 100 different states for it. And we also want to be careful about how many parents are in it. So in this one, we've kind of kept it down to 2 parents for each node there. If you're getting more than 5, then you're pretty much in danger territory, or I'd say you're pretty much in danger territory here. But what happens within this node here is every extra link that we put in there will really increase the complexity of the CPT that we need to put in here, which we'll come into next.
If you never connect that tree condition node to anything, why have it?
Well, I think for this one here is it's a good indicator of what's actually going on with the drought conditions and rainfall, or it might actually be an output node. We might be measuring how good this system is going on, not just native fish abundance, but the tree condition. And I think that was the suggestion. I don't know if it was in the text. I always read it as being that native fish was the important bit.
Concerned that the trees.
So there's concern that the trees and the native fish will be affected by the drought conditions and crop pesticides there.
So we're concerned about the trees as well?
So we actually are, for our output of how well the ecosystem is going there, we want those types of things in there. The other thing is that tree condition can inform us about the the fish population in other ways, which we'll get into a little bit later. I'm going backwards, Dan. So we've left out arcs, as we've been waffling on for the last little bit. You have another question?
Sorry, in the table, what I can see in the table is a fuzzy kind of presentation.
Sorry?
What I can see in this table is a fuzzy kind of presentation. And up to here, I can see this network is exactly same as the fuzzy cognitive maps.
Yes.
And I cannot see the difference between fuzzy kind of, you are using fuzzy kind of presentation here, but I cannot see the relation between probabilistic kind of.
I don't feel confident enough to talk about the fuzzy stuff to actually answer that type of question. But
yeah, exactly. I don't want to talk about fuzzy cognitive map, but I can see, you're presenting here, what you're talking here is exactly fuzzy cognitive maps. It's not a Bayesian network based on my understanding.
Yeah.
So I want to know that how do you present it, for example, the possibilities of, for example, the amount of each variable here. For example, do you give any specific number, a specific percentage, or you're just using this kind of
you're
table?
talking about how we define
Yes,
each of the
yes,
states
yes,
and
exactly.
stuff like
How
that.
do you-
Well, it varies, and that's one of our kind of knowledge engineering problems that often people aren't very good with actually specifying this type of stuff. But yeah, you're right. When we're doing that kind of definition type thing, we should be thinking about this. So when we're talking about a high native fisher population, how are we going to define that? Because there might be a whole lot of different things about how much fish there are and the general genetic structure of the population, and So in this case, I think we call it native fish abundance, so we might define it as amount of fish per square metre or something like that.
What kind of probabilistic relation do you use, for example, for defining each variable, and what is the relation between probabilistic theory and the variables and defining variables, the relations between the nodes and the network,
Yeah. So you're talking about documentation, is that right? Or?
Not documentation. I'm talking about defining the network and what is this based on. For example, do you have any weights on the relations, or how do you decide to go, for example, to pesticide in river or river flow or tree condition? It's based on a fuzzy information here, but you are talking about probabilistic.
Yeah, I think I might. Can we talk about this during the break? And
Yeah,
because
sure, why
I'm
not?
not 100% certain. Okay. All right. So as we were discussing with these different things here, we talked about different possible arcs in there. So we've left out things about pesticides and tree condition. So another thing that we suggested is the pesticides actually might have a negative impact on the tree condition, and there was no influence going through that as well. There's no other representations of the tree health, so there might be other things in the soil structure and stuff like that, which we just didn't put into the Bayesian network at all. And basically we've just got some, we're trying to keep it simple and be lazy. We don't want to put everything into there because it's, this is smart laziness, or we might just not know what these other types of things are. And when we don't know what we do that, we can just capture that into the uncertainty of the tables as well. So we can put a different sort of, how we put our numbers in there is going to put that. So we get summarising uncertainty within the links between drought conditions and tree conditions for these other causes of tree health there. And generally we do these documentation, and we'll say what we decided to omit and why we omitted it and when we think it might actually be appropriate to put it back into there in the future. I try to avoid using this terminology. I keep on slipping into it, but when we're talking graph theory, use this family metaphor. So when we're looking from causes to effect within a Bayesian network, we talk about the causes being parents of the children, which are down causal the pathway, and we have ancestors and descendants going through the tree. And we also have this tree analogy. We have the root nodes, which are the ones in this case, the ones at the very top here, with no parents. So we've got an upside down tree here. We have our root nodes at the very top, and we've got our leaf nodes, which are the ones which don't have any children coming out of it. So we often use this terminology. And yeah, often what we'll do is when we want to lay out these Bayesian networks, it's good to sort of think about how we're actually doing it so people can actually read it as well. So generally what we do is we put our root nodes at the very top and then leaf nodes going down there, or it can go from left to right. Basically it's like how we might read a book. And although we can use whatever type of layout and it's still going to work as a Bayesian network, but say for this one here, which is just doing a jumble type thing, we lose one of the really good advantages of Bayesian networks is that it's understandable. It's harder to interpret and read what's actually going on with this Bayesian network when we don't have a proper sort of like causal story ordering going on there.
Usually root nodes are the input data, yes?
Usually, but not necessarily, but often that is the case. And it's something that I'll talk a bit more of knowledge engineering tomorrow about how, you know, when we come into design these Bayesian networks, it's good to start thinking about where those evidence and where the inputs are going to go in. But generally what we'll do, and with this type of case here, is we'll put in observations about pesticide use and drought conditions and annual rainfall and then work out stuff down here. But often we might actually do it the other way as well. And that's one of the powers, that's why we use Bayesian networks to do that.
Kind of prediction, for example.
Yeah. So we're going to talk about that soon, which after morning tea. Okay, so the next one is the conditional probability tables. Now, generally when we're creating Bayesian networks, all this stuff, the identifying the random variables and the causal structure and stuff like that is pretty much the fun bit here. And when we're doing expert elicitation workshops, people can tend to get really enthusiastic about that and what links we're going to put in there. And people will like to put in, you know, when they would like to argue why we might put this particular link in there. And we often will end up with a rather complicated network. And then we come to the next bit, which is these quantifying these relationships. And it's very worthwhile thinking about this stuff ahead because this is where things start getting a bit really difficult and burdensome. So we have this idea of the conditional probability table. So our CPT quantifies the effect of appearance on a node. So in this particular case here, which is down at the bottom of our node here, native fish abundance is directly influenced by pesticide and river flow. So we have this node of the conditional probability table for fish abundance given pesticide, river, and river flow. So here's an example one that we kind of whipped together. I think this was done with some sort of consultation with somebody who was an expert. But it's just basically a toy Bayesian network here. So we have a table here. We have our two parents here, pesticide and river flow. And we have our fish abundance here in the states of fish abundance. So we look for each of these different combinations of parents here. So if pesticide and river is high and river flow is good, that's our best situation. We say here, that's not our best. Our best situation is when the pesticide is low and river flow is good. We get our 80% chance of high fish abundance. Why is it not 100%? Because there's other stuff that's going in the system which we haven't put into the model. We don't know about it. There might be somebody going around shooting the fish or something like that. We didn't put that in the model. We have to account for that uncertainty within this number here. And then we have some other probability for it being medium and probability for it being low. Now this is like, all these add up to 1. So each row in this table adds up to 1. We've got our worst case situation, which was pesticides high and the river flow is poor, and we're saying that there's a 1% chance that there's going to be good there. Again, it might be the case that somebody's come in and just chucked in a whole lot of fish there and we just have a good population, which is not sustainable here. But far more likely it's going to be low, given this situation here. And then we've got the in-between type of states there as well. Now, it's important to notice that as I add another parent in here, this table is going to grow exponentially. So we put more and more parents into there, more and more states, this table is going to get really, really big. Now, if we've got data, if we've got lots of data, that's generally okay. But if I'm relying on an expert to sort of give me these numbers, I mean, even doing a table this size is quite tiresome for experts as well. So when we're making those decisions about what links we want to put in and how much states we want to give to these nodes in those previous parts here, we need to be thinking ahead to what these tables are going to look like. And at some point you will make a table which is too complicated. That happens when you do Bayesian networks. So this is all, each row is the conditional probabilities, add to 1, and we've got this exponential thing here, so we can just see this in action where we've got adding binary nodes here, and every time we add a binary node, the table's doubling in size. So we have our our probabilities for our root nodes are our prior ones, and that just has one row. So we don't have any parent combinations to actually do the stuff here. So in our native fish model, the rainfall was our root node, or prior one. So we just put some prior probability. So before we know anything, we expect that there's a 70% chance that we're going to have an average rainfall year. 1% for above average and 2% for below average. Now, for after morning tea, we're going to start playing with the Bayesian network. How are we going with? Are we almost with the coffee here already?
10 minutes.
10 minutes. Okay, cool. So we'll start playing around with this, and we'll actually give you this Bayesian network, and you can start looking at these tables and critiquing it as however you want. Now, I find this slide's a bit boring. I think the interesting one here is with causal influence. Actually, Eric, do you have anything that you want to say about? So we're talking about here with the causal influence here, where we have a table where we've got these two different parents here, but you can see that the table for pesticide in the river is high is the same as the table for pesticide in the river is low. So even though we have a link within the network there, that influence can actually be totally washed out within the table here. Now, as I understand it, one of these projects that you've got here is you want to actually measure how much that influence is going on there. So in this case, it's a zero influence, but there's some degree of influence.
Yeah. So one convention typically would be that if the variable is irrelevant, you wouldn't actually have the arrow going from pesticide to fish abundance, would you?
Yeah, well, that's it. This point is here. I can put the arrow in there, but it's actually written out by the in the table. So just because there's arc in there doesn't mean that there's actually anything going on with it.
Yeah.
Yeah.
Yeah, that was my question. Can you guess the model according to the data? You have lots of data.
Yeah, well, and that's something that, there's lots of techniques for learning the model from the data, which is stuff that Kevin will talk about tomorrow. And if we've got the data, that's really good. Yes. Yeah. I don't know if there's anything to say on this one. I find the slides a bit.
Well, I think I'd be distracting you, but just the flow of it. Have you talked about the difference between causal interpretation and a non-causal interpretation? So Bayesian networks intrinsically mathematically adjust probabilistic relations, where the arrows don't have to be in a causal direction. But for many practical problems, it's useful to have the causal directions, and that's going to be our emphasis for reasons which there are many reasons for this, and we can talk about that at some other time. In fact, maybe I'll talk about that on Thursday.
Mm-hmm.
But mostly you should assume these arrows are supposed to be oriented in a causal direction. And that doesn't stop you from making anti-causal inferences. Like if you have a disease that has some symptom which is an effect of the disease, you see the symptom and then infer that you have the disease going the other way up against the direction of causation. Xin Hang's project is about kind of summarizing the effect of one variable on another using mutual information. So that's because the causal relations can be quite complex. So if you want something that's like a correlation coefficient, then you might use mutual information, and that's what she's implementing.
Right.
But there are also some quite complex definitions in the philosophical literature of when one event was the cause of another event. That gets quite complicated when you have two things, either of which would have been sufficient, for example, and there's a whole lot of scenarios. So Judea Pearl, for example, has put forward a definition with the philosopher Joseph Halpern, and that's one of the very common definitions. When Mathieu is working on ways to interpret a network, then one of the things we eventually want in the software is something like Pearl and Halpern's definition for individual events, and also Xin Hang's sort of measure of, in general, how much a variable influences another variable to kind of sensitivity analysis. So there's a lot you could say about trying to understand the causal relations that are on the face of it, they're all in there, but then to actually sort of get to grips with it mentally is harder than it looks.
Explaining what it like.
Yes, so you always have things like screening off, where if you have a child and then an intermediate variable and then an ancestor, if you know the parent Yeah, that's right. So some of that stuff is just in any Bayesian network, causal or not. But the distinctive feature, one more thing, the distinctive feature about the causal interpretation mathematically is that it predicts the result of intervening. So were the system to remain the same and you were to actually actively get in there and change something, things causally downstream would change, things causally upstream would not change. Right? That's a prediction that the causal network makes that a non-causal network does not make.
Yep.
So there's a specific possible world of interpretation of a causal network.
Yep. So we'll talk a bit more about that in a short bit. But one of the other things with the causal interpretations, if we're using experts and stuff like that, it's more of an intuitive understanding of the causal probabilities that we're pulling out.
That's right.
As well. So yeah. Getting back to this. Okay, so we've got our Bayesian network. It's got a set of random variables. We've got directed arcs between it, and I quickly went through this whole painful task of parameterizing the Bayesian network for all these probabilities as well. The last thing here is that a Bayesian network has to be a directed acyclic graph. So this came up when we were talking about the tree condition, river flow, cycles going on there. Now your system might have a cycle through it, but our Bayesian network can't have it. Or it can actually. There's some little tricks that we can actually do to handle these feedback loops. So here's another example here with socioeconomic status and education going around, but we can't do feedback loops. We can use dynamic Bayesian networks, which I'm going to talk about tomorrow. Okay, so we've got a summary for Bayesian networks. We've got made up the nodes, particular variables, the arcs and the CPTs. And we have, after we've taken all these efforts to actually create this Bayesian network, we have a model of the problem domain and we can do stuff with this model now. So what we're going to talk about after tea break, I think, is start talking about using the Bayesian networks after we've created them. So I think the coffee should be here pretty much any minute. So this is a good point to stop. Okay.